So from the first days of the class, I said that there were three characteristics of a communication system that has to be traded off in order to come to the best match for a given situation. So those three are, of course, the bit error rate versus signal to noise ratio, or what I call the power efficiency. There is, of course, the cost or complexity of the system, and the third leg of this triangle is the spectral efficiency. And that's what we'll be talking about today and what will be the focus of some aspects of the homework assignment. So spectral efficiency, what does it mean? Well, I'm going to have a certain amount of spectrum that I occupy in order to make my transmission. And I would like to send as much data as I can through that occupied bandwidth. And so spectral efficiency is like, how can I push to send as much data as possible, given that I have a certain amount of spectrum available? So in order to answer this question, I'm going to start with the concept of frequency shift keying. Because what is frequency shift keying? Frequency shift keying is having a center frequency of the signal determining which symbol is being transmitted. And so here it's very clear that the symbol occupies a certain bandwidth. And so this will give us an easy way of attacking the problem of how tightly could I pack my information in the spectrum. Because in this case, it's quite clear that each frequency is a symbol. And so we'll start with this, but even though I'm concentrating on MFSK to begin this discussion, we're going in a direction where we'll have a general benchmark for any modulation format to see how efficient it is to be able to compare across modulation formats. So in particular, for MFSK, we'll be looking at the fact that we consider this to be an orthogonal modulation format, and that's because each symbol is orthogonal from the other. Now, I can imagine that orthogonality would be easy if my frequencies were really well separated. I sent a little bit of information at 1 megahertz, a little bit more information at 20 megahertz, and some more information at 90 megahertz. Well, they're so far apart, and if the information content was moderate, they would have no problem. But that would be very wasteful in the occupied spectrum because I would be occupying a great deal of spectrum. So the question is, what is the minimal separation we can have for our carriers? And we can imagine these symbols becoming closer and closer in frequency, and at some point, intuitively, they're going to start influencing one another. And because they are influencing one another, they will no longer be orthogonal. And therefore, we're looking for the minimal carrier separation in order to maintain this concept of orthogonality. So now once we get this idea, how closely can I pack FSK? That, as I said, will give us a benchmark that we can use for other modulation formats. So let's start out with orthogonality. How did we define orthogonality in our vector space? So for MFSK in particular, we said that each one of these symbols would be represented by a tone, a cosine, at a certain frequency, and which frequency it was determined which symbol was being transmitted. And in our orthogonality criteria, that means that the inner product is equal to 0. So we assumed that these cosines were orthogonal to one another, that their inner product was 0. So this is our assumption right here. And because of this, of course, we said they're orthogonal. That means that each one of the symbols is a basis vector, and we went from there. When we did our error probability analysis, we used this assumption in the derivation of the probability of error. We assumed that in a branch where the signal was not transmitted, so I have a branch that's tuned to the first frequency, when the second frequency was actually sent, then the branch with the first frequency would see nothing. It would only be noise. And why is that? Because we did a correlation with cosine omega 2, and if I had a cosine omega 1, that would give me a 0 because they are orthogonal. So how can we assure orthogonality? And it comes down to what choice should we make of these pairs of frequencies to assure that this orthogonality assumption is valid? And that's the question I'm going to answer now. So when we have a branch in the receiver for FSK, we're going to correlate one of the tones, and what we're assuming is that we're going to have a second tone there, and of course we want their inner product to be 0. So what happens here is we're going to just look at the trigonometric identity to help us break down this correlation to see what we're requesting. So let's say that I'm going to put in an arbitrary phase offset here, theta, and I'm going to do that because I'm going to first do my calculation for non-coherent, in this case binary FSK, non-coherent. That means that there is some phase offset and that I do not know what the value of that phase offset is. Once we get our conclusion for non-coherent, of course then we'll be able to put theta equal to 0 and say, okay, now I have the answer for coherent when I do know the phase difference and I set it to 0. But we'll do the more general case, which would be the non-coherent case. So I have this offset theta, and the first application I can make of the trigonometric identities is the one that breaks out the sum, the cosine of a sum of terms. And of course the cosine of a sum of terms is the same as the product, cosine theta times the cosine of the other argument, and the other one would be sine times that cosine. Sorry, sine times that sine. So cosine, I guess I should have just written it here, alpha plus beta, cosine alpha, cosine beta, minus sine alpha, sine beta. Yeah, that's a lot clearer than what I said. So I apply that here as my first manipulation. And of course, later I have sine, excuse me, sorry. So we have the next manipulation I have is I have a cosine times a cosine, and I sort of do the sort of like the inverse of this relationship. And because of that, the product of two cosines can be written as the sum of the sum and difference of the arguments. So you can see here that the cosine times the cosine, I turn into the cosine of the argument of the difference. That would be this one. And the cosine of the argument of the sum of the arguments. So the light green goes that, this green goes to that green, and then of course this term goes here, a relationship for the sine times cosine. So I start with the correlator for the non-coherence case, and I end up with these two relationships, cosine times an integral minus the sine times an integral. And let me just write that again. Those integrals, I just repeated it up here. So what I'm going to do next is evaluate the integrals. And so I know that the integral of a sine is a cosine, the integral of cosine is a sine, and of course we're integrating with respect to t, so the other parts become the constants multiplying t, and of course I have to divide by those. So this is what we get for the integrals. And these integrals are definite integrals, and they are to be evaluated between 0 and t, the time of a symbol. So I have a sine of the difference divided by that difference in the argument, sine of the sum of the arguments divided by the multiplicative factor of t, in this case 2 pi times f1 plus f2, and the same thing with the cosines. So now simply do the evaluation between 0 and t, and of course there's some simplifications we can make, that the cosine of 0 is 1, sine of 0 is 0, and so we end up with this representation I give here. And so we have cosine of theta, which is multiplying this terms, one in the difference between the frequencies and one in the sum of the frequencies. And the same thing applies to the sine, except that you can see that in some cases we're subtracting 1 because that was when we had cosine of 0. Okay, so we have a simplification here. And remember, what we're trying to do is find what choice of F1 and F2 will assure that this is 0. So we go on now. And the first thing I notice, again, I just repeated those equations here so we would have them again. First thing I notice is that when I look at the double frequency term, or the sum of the two frequencies, I know that this is going to be much, much greater than 1. So for all practical purposes, these terms divided by the double frequency, they're like going to 0 compared to the other terms. I mean, they're just really, really small. So the first thing I'm going to do is neglect those. So we're going to get rid of these because they're so small. And so what I'm left with is this equation where I have some cosine theta times a sine over its argument, and then I have a sine theta and I have a cosine minus 1 divided by its argument. So now they have the same denominator, so I can combine denominators, and what I want to get is for this numerator now, let's concentrate on the numerator because it's the same denominator, I want it to be equal to 0. And I want that to be 0 for all theta, because for non-coherent detection, I don't know what theta is. So I want it to be true for all of them. So now my question is, how can I force the numerator to be 0 no matter what the value of theta? So I repeat the equation again here, what we're looking to find. And the first thing I notice is that if I want the sine, I want this to be 0 no matter what theta is. So I have to have what multiplies sine theta. I don't know what theta is, so I don't know what sine theta is. So what I have to have is that what multiplies the sine theta, that should be 0. So I look at what's shaded in blue here, and this should be equal to 1, because if it's equal to 1, then what multiplies sine is 0. So I want that cosine to equal 1. And of course, the same applies to the other term. So I want that sine be equal to 0. Now, if I take those two requirements, the cosine of 2 pi t times the difference in the frequencies is equal to 1, and that the sine of 2 pi t times those frequencies is equal to 0, that means that the 2 pi t times the difference in the frequencies should be equal to a multiple of 2 pi. If it's a multiple of 2 pi, then I will get 1 for the cosine, 0 for the sine. So if I do a little math, that means that the difference between the two frequencies must be equal to an integer divided by t. Now, if I want to have the minimal separation, then I want n to be as small as possible. I want f1 minus f2. I want to pack them as tightly as I can and still have them be orthogonal. And that would be minimal at n equal 1. Now suppose we change to the case of coherent. When we go to coherent, now it doesn't have to be true for all theta, it only has to be true for theta equal to 0. For theta equal to 0, that means that sine of 0 is going to be 0, so this term is going to go away. So that means that we only have to worry about what multiplies the cosine and force that to be 0. So this is what multiplies the cosine. So we want sine of 2 pi t times the difference in frequencies to be equal to 0, which means that we want that argument, 2 pi t times the difference in frequencies, to be equal to a multiple of pi. Not a multiple of 2 pi, but just pi. And so now the separation that I'm requiring is that it be n divided by 2t. And now if I see that the minimal separation, again, is at n equal 1, then I'll get a new requirement for the separation. And indeed, I'll have a factor of 2. It'll be tighter spaced because I used coherent detection. So to summarize, for BFSK, binary frequency shift keying detection, we found that for non-coherent detection, the minimal separation is 1 over t. For coherent reception, the minimal separation is 1 over 2t. So right away, I can see one of my trade-offs I can be more spectrally efficient because the separation could be half as much. So I could pack them in twice as much if I use coherent detection versus non-coherent detection. And that, of course, coherent is a more expensive solution than non-coherent, but we see it is also more spectrally efficient. So this has been for binary. And really, if I want to exploit this as a benchmark, I want it for M-ary. It's a little tricky, not much. There is a homework problem or an exercise at the end of the chapter with Sklar. I didn't assign it for homework, which sort of asks you to develop it. And I've had questions in the past about that. So I'll take just a couple minutes to tell you how you would do the extrapolation to M-ary case. Now, right up here at top, very important, I'm assuming I have a rectangular pulse in time. So a square pulse in time, which of course means in the frequency domain, and this here is the frequency domain, I have some sinc functions. So the spectrum of the FSK signals are sinc functions. So suppose that I'm doing non-coherent detection, and I know that I've found that the minimal separation is 1 over t. So here I've drawn it as a separation of 1 over t between F1 and F2, sort of the center of their main lobes. And we can see that we have this orthogonality. Excuse me. And now if I looked at coherent FSK, the same rectangular pulse, of course, now they could be more tightly packed. So the frequency separation is 1/2. And you can see that we're going through zeros at different times, but they're still orthogonal. So as I do the extension to the M-ary case, this will be covered in different sections in the book, in Chapter 9 in particular, where we start talking more explicitly about bandwidth efficiency and indeed by capacity. And that will be the subject of the next lecture. Now we're going to concentrate on that bandwidth efficiency. So let's take this non-coherent case. Again, rectangular pulse in time. And so I have, the minimal spacing is 1 over t. And so every time I add a symbol to make up the M symbols in the constellation, I'm going to space them at 1 over t. So if I look at this and I sort of use my bandwidth to be the main lobe, I can see that if I start at one main lobe and go to the end main lobe of the last one, that the total spacing is going to be m plus 1 over t. So that's the occupied spectrum, let's say, our definition of occupied spectrum for this rectangular pulse in time. And if we look at the coherent case, because they're tighter packed, when we do the same exercise, we're going to get the total occupied bandwidth to be m plus 3 divided by 2t. Now, in this assumption, we had a rectangular pulse in time. And then this is the right answer. This is how much they're packed, what they occupy. And of course, since the sinc function goes on forever, I had to say, well, I'm going to define the bandwidth as being the main lobe. So what we're going to do is when we want to come up with a benchmark, what is like the most efficient you can be? Well, in that case, we wouldn't use a rectangular pulse in time. If we wanted to be the most efficient we would be using an ideal Nyquist pulse, which of course is a sinc function in the time domain and a rectangle in the frequency domain. So again, when I want to get a benchmark for spectral efficiency, what I'm going to assume is that I have done everything I could possibly do to occupy the least bandwidth possible. And one thing I have to do is to use Nyquist pulses. So here in the time domain, not a rectangle, but a sinc function, which means that if I look at the frequency representation of that signal, I would get a power spectral density that was rectangular between minus 1 over 2t and 1 over 2t. So the total bandwidth would be 1 over t. And t, of course, is the time of one symbol. So this is the minimum bandwidth I can occupy. So what happens to when I'm counting for M-ary when I use this other assumption that I'm using the most spectrally efficient possible signaling? So I take my rectangle, and once again, let's take the the coherent case first. And the separation between the center frequencies of these rectangular power spectral densities is going to be the minimal separation, which is 1 over 2t. Now if I do the measurement, if I put m of them, I'm going to get that it's m plus 1 over 2t. The last time I had a 3 here. What's changed is for the rectangular pulses, it's like I occupied an extra slot. So this is the most efficient I can do with FSK, coherent detection, ideal Nyquist pulse. This is really the minimal occupancy I can get for this frequency. So now I'm going to define bandwidth efficiency. And the bandwidth efficiency metric that I'm going to use is I'm going to define it to be the bit rate divided by the occupied bandwidth. So I want to send as many bits as I can, but in a given bandwidth. So first of all, the bit rate is just 1 over the time of a bit. So during the time of 1 bit, I send 1 bit. So the rate is 1 over TB. So now I have this expression in terms of the bit rate, or the bit interval, and the bandwidth. And so what's interesting now is, of course, that here I have a bandwidth that is sort of related to the time of a symbol, which is why I like using the Nyquist pulse. It makes everything nice and unambiguous. So I'm going to go back here and recall for you that the time of a bit is related to the time of a symbol by just log 2m, that's the number of bits per symbol. So let's look at coherent MFSK. Each symbol is set on an independent frequency range, and we know that the minimum spacing we can do is to put ideal Nyquist pulses, and so we would get that the efficiency of MFSK, well, we're going to put 1 over, well, here we have m plus 1 over 2 times TS here. And I'm going to say that that's m plus 1 over 2 TB log 2m. So this is W, and of course I'm going to put that in the 1 over W. And when I do that, I'll get the 2 log 2m in the numerator, the m plus 1 in the denominator, and of course the TB's cancel. So I come up with a nice, simple expression for the spectral efficiency of coherent MFSK. And it's 2 times the log 2 of m, and it's divided by m plus 1. And the units for bandwidth efficiency or spectral efficiency is in bits per second, that's the rate, R, per hertz, that's the bandwidth occupied. And of course, 1 over seconds is the equivalent of hertz, so this really becomes kind of dimensionless. However, to keep it clear whether we're talking about bits or symbol efficiency, we're going to definitely call the units bits per second per hertz. So that was for coherent. So what happens if we do a similar calculation, but this time for non-coherent? So once again, assume that we have the ideal Nyquist pulse in the time domain, i.e. a sinc, which means that in the frequency domain we have these rectangular spectrum, most compact possible. Now I have to keep the separation at 1 over t. So now they're completely not overlapping. And because they're not overlapping, intuitively it makes a lot of sense. Won't matter about the fact that they could be out of phase from one another, because when I do a perfect filter bank, there'll be energy only in one, because there's no overlap in the spectral content of different symbols. So makes perfect sense. And now we look at the total occupied bandwidth. In this case is m over t. So now I can use this in my equation for the spectral efficiency. And in this case, I have m over ts, and of course I replace that by m over tb log 2m, and I substitute this into this equation, and I get that the efficiency of MFSK is just log 2m divided by m bits per second per hertz. Of course, the difference is this factor of 2, as we suspected before, that we have this twice the spectral efficiency if we use coherent detection. So let's try and figure out what these two terms of a logarithm in the numerator and linear in the denominator, where this comes from for this modulation format. So of course we have the relationship between TS and TB here, that the for binary, for instance, log 2m would be 2, log 2m would be 1, and the bit time and the symbol time would be the same. Now suppose that we fix the time of a bit. So like we're fixing the bit rate. I want to achieve 1 megabit per second. I'm fixing TB, and I start looking to what happens spectrally when I start increasing m. So in this illustration, TB stays the same, but of course as m gets bigger, then TS is getting bigger. And because TS is getting bigger, that means 1 over TS is getting smaller. And that means that the occupied bandwidth is getting smaller for each one of the frequencies. So if we start with FSK, in this case, this is symbol 1, this is symbol 2, and they each occupy a fair chunk of spectrum. Now when I go up to FSK and I want to use more bits, excuse me, I'm going to use more bits per symbol, but I'm still sending the same information rate. The rates of bits is the same. So first of all, QFSK, things look pretty good. I can see that now I have 4 symbols, but each one of the occupancy has gone down. And now let's look at 8FSK. And again, I'm going I'm getting smaller here from the widest to smaller, and this is getting smaller based on the logarithmic decay. But I'm getting more of them, and that is growing linearly. Here I had 2, now I have 4, and here I have 8 slots that I'm using. And you can see that as m gets bigger, although each one of the frequencies is getting smaller, I'm getting more of them, and so I'm actually expanding and using more frequencies as I increase m. So the bit rate is staying the same. I'm trying to increase the number of points in the constellation. I know I can increase them without increasing the bit error rate. However, as I do increase m, although my bit error rate is not getting worse, my spectral efficiency is getting worse because the TB is set, but I'm occupying more and more bandwidth.